Hey everybody, this is Emily. So this video is all about confidence intervals. So we're going to use what we've learned about the normal distribution and the empirical rule, and we're going to use that to construct interval estimates for the first time. So in the beginning of this video, I'm first going to teach you how to do this using the normal distribution, using what we say is a known population standard deviation. Sometimes you don't know the population standard deviation, so then you'll use, as I'll show you at the end of this video, a student's t-distribution. All right, buckle up. Let's go. All right, so as we're diving into the confidence interval material, let's do a flashback to parameters and statistics. Remember, parameters are numbers that describe the population. So for example, if we were looking at the average number of points earned by math students in all math classes, so that's all students in all math classes, would be looking at the population. But remember, the statistic is the number that represents the property of the sample. So in that case, we would be talking about a random selection of those math students, and then the statistic would be the average number of points earned by math students in our sample. The sample mean x bar is what we call a point estimate for the population mean mu. What do we mean by point estimate? It means that there's a singular value that we're using to estimate a population parameter. So remember that each of mu, that's the average of our population, and the standard deviation of the population, that lowercase sigma, both of those are called parameters. Parameters are pieces of information about a population. The sample standard deviation, S, is the point estimate for the population standard deviation written as lowercase sigma. So each of X bar and S are called statistics. Remember, statistics describe samples. We use X bar and S as points to estimate the population parameters, mu, the standard deviation of the population. In other words, they are point estimates of population parameters. These point estimates are important in inferential statistics, right? We use our sample data to make generalizations or inferences about an unknown population, right? This process of taking X bar, or our standard deviation of the sample, and using that to make inferences about our population, like mu, the average of our population, or the standard deviation of the population. That part of statistics is called inferential statistics. The sample data help us to make an estimate of a population parameter. So far, we've learned how to calculate some single value statistics, which we call point estimates. So the ones we've learned about include means, sums of sampling distributions, means of sampling distributions, probabilities of events, and probabilities of a mean or sum falling above or below values under a normal distribution. Y'all are point estimate pros already, and you didn't know it. So now we want to build upon our skills to go from just point estimates to creating interval estimates. We realize that point estimates are a single value, and they're most likely not the exact value of the population parameter, but probably close to it, right? Well, how close? And what if we wanted to be pretty sure about how close our point estimate was to the actual value? So after calculating point estimates, we construct what are called interval estimates, called confidence intervals. A really simple way of thinking about this is that we're going to center our mean, right, in our normal distribution that we've been talking about throughout the semester. We're going to center that mean and then create a range around it. And we're going to identify mathematically a confidence level. So we want to be maybe 95% confident is a really common confidence level to set. We're going to perform some statistical operations. We're going to put some bounds above and below our mean to create a range so that we can say that we're 95% confident that our actual population parameter falls between these limits. So again, this is called a confidence interval. Again, it's another type of estimate, but instead of being just one number, it's an interval of numbers. It provides a range of reasonable values in which we expect the population parameter to fall. Now, there's no guarantee that a given confidence interval does capture the parameter, but there's a predictable probability of success. So how does the empirical rule work when shaping our confidence intervals? Again, remember that in statistics, we're taking samples. And in the last few videos, we've worked a lot with samples. We've set up entire sampling distributions, like taking 50 samples over and over of a population, calculating the mean of each sample, and then plotting those results in a histogram, sampling distribution of the means. And we've learned that sample means and sums tend to follow the properties of the central limit theorem, such that they are normally distributed. Remember that when data are normally distributed, we can use the empirical rule to describe the percent of data that fall between a certain number of standard deviations of the mean. A really common confidence level to set is 95%, right? In statistics, in science, in lots of different fields, we accept error of about 5%. So 100% minus 5% error, we often choose to be about 95% confident. And that 95% confidence is connected to the values lying between minus 2 standard deviations and plus 2 standard deviations of the mean mu. So if we want to be 95% confident, we should include the values that are within 2 standard deviations of the mean. That helps us construct our confidence intervals. And this applies to sampling distributions too. Remember, in a sampling distribution, 95% of the sample point estimates lie between minus 2 standard deviations and plus 2 standard deviations of the mean mu, or in other words, within 2 standard deviations of the mean. In other words, if we took a point estimate like the mean of the sample x bar, there's a 95% chance that this sample mean will fall within minus 2 standard deviations and plus 2 standard deviations of the actual population mean mu. So whenever we take a sample and we calculate that statistic for the sample, we can construct what's called a confidence interval around it. And we can assume that 95% of the time, our population mean, mu, will actually occur a confidence interval around it. I want to introduce you to some of the things you're seeing here. See this little fish-shaped character? That's called alpha, and we're going to talk about alpha in a little bit. And you can see that we're saying 1 minus alpha is 0.95. Alpha is what many people call our P level, which you may have seen in published social science papers. So let's look at a confidence interval example. Let's say that we ask 100 students at a university how many ounces of water each individual drinks each day. So that's a small survey, and we're estimating how many ounces of water each student drinks each day in the total university population. So let's say that our sample data shows that on average, our class drinks 45 ounces of water each day with a standard deviation of 5 ounces. So let's construct a 95% confidence interval. That's going to include 2 standard deviations above and 2 standard deviations below the mean. Now, when we're working with problems like this, we're going to be given a population standard deviation. In this case, we were told that the population standard deviation was 5. So we need to use S, the standard error of the mean, which is calculated as follows. The standard deviation divided by the square root of n. We take 5, and we're going to divide that by the square root of our sample size. Do you remember? It was 100. So that simplifies as follows. 5 divided by 10, which is equal to 0.5. Then what we do is we calculate this very simple plus or minus logic. You've probably heard in news reporting, in statistical poll reporting, that we usually give a value and we say plus or minus a value. So for example, the average weight was 100 pounds plus or minus 5 pounds. So we take our mean x bar, and first we're going to add 2 standard deviations, and we're going to make sure to use S, the standard error of the mean. So we were given x bar is 45, and we're going to plug in our standard error of the mean. So 2 times the standard error of the mean, 45 plus 2 times 0.5 is 46. And then x bar minus 2s, again using the standard error of the mean, s. That's 45 minus 2 times the standard error of the mean. So 45 minus 2 times 0.5 is 44. We are 95% confident that the unknown population mean of ounces of water drunk by individual students each day is between our lower number, 44 ounces, and our higher number, 46 ounces. You can also write it this way, that 95% confidence interval is, and you put in your range within parentheses, 44, 46. What does that mean for us? Let's draw out what this means. So we were given a sample mean that this here is 45 ounces. And then I'm going to go out 2 standard deviations above the mean and 2 standard deviations below the mean. And I'm going to get this 95% confidence interval by shading in the 95% inner area underneath the curve symmetrical about that sample mean x bar. Again, we were given the population standard deviation, which was 5. So then we used the standard error of the mean, lowercase s, that's the sample standard deviation. And by using that information, we took 45 plus 2 times s, which we learned was 46, and then 45 minus 2 times s, which we learned was 44. So we had our point estimate, x bar. That's a good estimate. That's a single point. But now we're constructing an interval around it, saying, okay, well, we know that it's probably around 45, but we're 95% certain that actually the true value of the population mean will fall somewhere between 44 and 46. And again, we're talking about ounces of water drunk on average by a student population. There is a 95% chance that the interval we calculated, 44 to 46, does contain the true mean of ounces of water of the student population. So 95% of the time, the sample that we have did and will produce a sample mean that falls within those 2 standard deviations of the true mean. However, there's a 5% chance that the interval we calculated, 44, 46, does not contain the true mean ounces of water of the student population. So our sample did not produce a sample mean that falls within 2 standard deviations of the true mean. This only happens for 5% of all samples because by definition, when we've set a confidence level of 95%, that means we're right 95% of the time. And that 5% of the time, we are going to expect that we are not right. So let's review these key points. When we're working with a confidence interval, we're creating it for an unknown population parameter, like the population mean, mu. And confidence intervals for some parameters have this form. We take the point estimate, like x bar, and we subtract our margin of error, and then a point estimate, and then we add the margin of error, just like we did before. X bar minus an amount, x bar plus the same amount. So that margin of error is going to vary. It's going to depend on the confidence level or percentage of confidence and the standard error of the mean. When you read newspapers and journals, some reports will use the phrase margin of error. You've seen that before. Other reports will not use that phrase, but they will include a confidence interval as the point estimate, plus or minus the margin of error. These are 2 ways of explaining the same concept that we're reviewing. The way that we're doing this right now is a little strange. We're going to unpack why. We're learning how to construct confidence intervals when a population standard deviation is known. Let's give away this punchline. That's kind of weird, but we're learning how to do this to first understand the theory. Why is it weird? Well, how would we know a population standard deviation if we didn't know the mean, right? It would be kind of weird, if not impossible, to know the average of a sample x bar, not know the population mean mu, but somehow know the population standard deviation, right? How would that happen? Well, what we're doing now is using the normal distribution, and we're going to say we're using large samples, and our practice problems give us the population standard deviation to work with. Later, we're going to learn how to use another distribution for the more common situation that we won't know the population standard deviation, and we'll get to that. So just know that if this feels a little bit strange for now, that's all okay. The main takeaway is first we're learning how to compute these problems using a known population standard deviation. So what we do is we use S, the standard error of the mean that comes from the central limit theorem. We take that known population standard deviation, and then we divide it by the square root of n, and that's what creates S, the standard error of the mean. And that comes from the central limit theorem, right? Our sampling distribution of the means is normally distributed. That means that capital X bar is approximately normally distributed with the same mu as the original distribution, but the standard deviation is going to be a little bit smaller, the standard deviation divided by the square root of your sample size. When a population standard deviation is known, we will use a normal distribution to calculate the error bound. That's how you're going to complete your practice problems this week. There's another probability to know called alpha, and it's related to the confidence level, which we often write as CL. We've been working with that 95% confidence level, right? When we construct that 95% confidence level, we take the area under the curve between 2 standard deviations below the mean and 2 standard deviations above the mean, because that accounts for 95% of the area under the curve symmetrical about our mean. So alpha is the probability that the interval does not contain the unknown population parameter. So it's the area over here plus the area over here. Let's talk more about this. So this area here that is shaded in is 95% of the area underneath the curve. That equals our confidence level. Now, alpha mathematically plus the confidence level equals 1, or 100%. So let's look at this mathematically. If we know that alpha plus 95% equals 100%, then we know that alpha is 5%. That's like saying 5% of our area underneath the curve and above the x-axis is not shaded in. But we distribute that between the two tails. So this area over here is alpha divided by 2. And this area over here is alpha divided by 2 as well. This small area is 5% divided by 2, which is 2.5%, this dark area shaded here. And over here we have the same amount. Alpha, 5% divided by 2, is 2.5%. So we can use the Bogner applet to get our z-scores. Remember, reading a z-score table is not fun to do, so I wanted to give you another way to do this that's faster and simpler and uses a visual. So let's use our old friend, the Bogner applet. We want to set up a normal distribution and calculate a z-score by setting it to the standard normal curve, right? So here we've got mu equals 0, standard deviation is 1, and then we're going to use this preference that's set in the circle, right? What it's saying is split the probability between the tails symmetrical about the mean. So you want to calculate what to enter in the red area by subtracting your confidence level from 100. So here, we're actually calculating a 90% confidence level by putting in 0.10. That's our total alpha, right? And what's returned is our z-score, the blue x value. That's what we're going to use to construct a confidence interval. So I want you to test, go to the Bogner applet yourself, and let's calculate a confidence interval of 95%. So here you'll put 0.05 in the red box, and then see what returns here in the blue box, x. I'll give you a second to do it. Did you get z equals 1.96? Exactly, it's almost 2. It's not quite exactly 2. Our 95% confidence level means that we have an alpha in proportion form of 0.05. That's what you enter into this box. And when you click away, you will get a z-score of 1.96. Awesome, that's what we're going to use to calculate our confidence interval. So let's put it all together. But wait, what was that about z-scores again? Why wasn't it exactly 2 for the 95% confidence interval? Isn't that what the empirical rule has been teaching us? I know, it's been rounding this whole time. Remember, we're constructing a z-score that has an area to the right of alpha divided by 2, and we'll call that z, a z-score, with the subtext. Remember, we kind of call that our little hashtag to remind us what the z-score is connected to. So z sub alpha divided by 2. We can construct a confidence level of 95% or 0.95 written in proportion form. So alpha would be 0.05 and alpha divided by 2 would be 0.025, again written in proportion form. So we will write z alpha sub 2. And so for 95% confidence interval, we're going to be looking for the z sub 0.025. Awesome. So what does that look like? It's almost 2 standard deviations below the mean and almost 2 standard deviations above the mean. And we're taking that area under the curve. That's our 95% confidence level, written here as a proportion, 0.95. So we're taking that probability under the curve, and then over here we have alpha divided by 2, accounts for this unshaded area, and this area is alpha divided by 2, right? That's this unshaded area. Exactly, so we're using 0.196 because we're being really precise using the Bogner applet of making sure we're capturing exactly 0.95 as a proportion, or 95% of the area underneath the curve. You're going to use this number a lot, so 1.96 will end up sticking in your head. So let's put it all together. What are our steps for dealing with confidence interval problems? First, you're going to figure out your x-bar, your standard deviation, and your sample size from the problem. And again, for these first problems that we're doing, we're going to be given the population standard deviation. Then you're going to calculate the standard error of the mean, and this is the formula. Take this population standard deviation and divide it by the square root of n. Then you want to figure out what your alpha is. So if you have a 95% confidence level, 100 minus 95 is 5. That's your alpha. And of course, you want to know what your alpha divided by 2 is. You're going to use your Bogner applet to find out what the appropriate z-score would be related to your confidence interval at hand. So the short link again for your phone or computer is bit.ly/Bogner app. The capitals matter here with a short link. And remember, you're going to enter the entire alpha, not alpha divided by 2, into that red box, as you saw in the previous slides. Make sure you select this parameter, which is saying make sure that we're putting the alpha probability into the tails. Step 3 will give you the z-score to use. Then calculate the confidence interval using all the components you know. Then you're going to use the error bound formula for the population mean when the population standard deviation is known, which is your z-score. Then you're going to multiply it by the standard error of the mean. Pretty simple. Then you construct your confidence intervals as follows. Take that given x-bar, subtract EBM from this step, comma, x-bar plus EBM from this step. And then you're going to write a complete sentence explaining the confidence interval. So here's your written interpretation, right? The interpretation should clearly state the confidence level, explain what a population parameter is and what's being estimated. So here a population mean. Then you're going to state the confidence interval and state both endpoints. Here's the formula to use. So we estimate with blank % confidence that the true population mean of, include the context of the problem, is between blank, and then include the appropriate units. So just for fun, let's make up a confidence interval example. Let's say that we estimated with 90% confidence that the true population mean of, the number of cups of coffee drunk daily is between 1.5 and 2.5. Now make sure to always include your units. In this case, it's cups. So again, to read that out loud, we always have this formula. We estimate with 90% confidence that the true population mean of number of cups of coffee drunk daily is between, and then you give two values, your lower value, 1.5, and 2.5, your higher value, and include your units, cups. All right, I want to point this out. This will be seen in your homework. What happens when you change the confidence level and the sample size? So here's the summary. When you change the confidence level, if you increase the confidence level, say from 90 to 95, that's going to make your confidence interval wider. So you'll have a wider range, a larger interval of values where it's possible for the population mean to fall into. Decreasing the confidence level will decrease that error bound and make the confidence interval narrower. So how does that work? If you wanted to be only 50% sure of something, you would have a really narrow range. That's okay if you don't need to be right, but you want to have a very precise and small interval. However, if you wanted to be super sure, you would want to choose a 90% or 95% confidence level, but that might mean you have a wider range. So you might be saying that we're not really sure how many cups of coffee are drunk per day. It's anywhere between 0 and 10 cups. Whereas if you had a more narrow confidence interval, you could say we're 50% sure that people drink between 3 and 3.25 cups per day, right? So you want to think, what do you value more? The precision of your interval or making sure that you're mostly right? Let's summarize the effect of changing the sample size. Increasing the sample size will cause the error bound to decrease, which makes the confidence interval narrower. This makes sense, right? Law of large numbers. As we increase our sample size, we're going to see more precision in our statistics. However, decreasing the sample size will cause the error bound to increase, making the confidence interval wider. So again, you want to think about justifying your information. Do I want to sample more people so that I have a smaller interval and more precision in my estimate? Or is sampling a lot of people going to cost me a lot of time, energy, or other resources, so I'm happier having a wider interval? If you ever needed it, you can directly calculate the sample size n that will give you a specific margin of error. All you do is flip around using algebra, this given error bound calculation. If you need to find the sample size, you use this fraction as follows, and you solve the error bound formula for n. You're taking the z-score, squaring it, multiplying it by the population standard deviation, squaring it, and then you're going to divide it by the error bound squared. This example shows us how you can calculate n, right? The right sample size that you would need to get a certain confidence level. So the population standard deviation for the age of Foothill College students is 15 years. If we wanted to be 95% confident that the sample mean age is within 2 years of the population mean age of Foothill College students, how many randomly selected Foothill College students must be surveyed, right? So we're trying to say we don't want a bound that's any bigger than 2 years of the true population mean age. We want to be precise. So how many people to get to that level of precision with our error bound? So from the problem, we know that our standard deviation of the population is 15 years, and we know that the error bound that's been given to us is 2 years, right? We've set the confidence level to 95%. The z-score for 95% confidence is 1.96, as we saw in a previous problem. If you don't trust me, go ahead and look at the Bogner applet. Then it's a plug and chug situation. Using the given formula, we're going to plug in our z-score and square it and multiply that by our population standard deviation squared. We're going to divide it by our error bound squared. Remember, people are full humans. We can't have a fraction of a human. So we need to round up. We always need to round our answer up to the next highest integer to ensure that the sample size is large enough. So we will use n equals 217. In a full sentence, that means 217 Foothill College students should be surveyed in order to be 95% confident that we are within 2 years of the true population mean age of Foothill College students. Let's use the following prompt. The standard deviation of the weights of elephants is known to be approximately 15 pounds. We wish to construct a 95% confidence interval for the mean weight of newborn elephant calves. 50 newborn elephants are weighed. The sample mean is 244 pounds. The sample standard deviation is 11 pounds. Now, what I've taught you so far has asked you to focus on only using the known population standard deviation. So we're going to forget that we know this information because we're going to focus on using our z-scores. So let's first identify the following. What was our given x bar? Yes, that's our sample mean, so it's 244 pounds. The standard deviation of the weights of elephants is known to be approximately 15 pounds, so that's our population standard deviation. Finally, we were given a sample size n of 50 newborn elephants. So in words, let's define random variables x and x bar. Remember, capital X is the distribution, so in this case, it would be the distribution of weights of newborn elephants. And x bar is our sampling distribution, so that if we took repeated samples of size 50 over and over of newborn elephants, and we took the average weight of those small samples of cute newborn elephants, that would be our sampling distribution, capital X bar. So the problem's asking us, which distribution should we use for this problem? The normal distribution. Why? We're going to use z-scores, and z-scores are associated with the normal distribution. We're using z-scores because we know the population standard deviation. So I'm going to say that we're going to use the normal distribution that uses z-scores to answer our error-bound calculation questions. So now I'm going to calculate a 95% confidence interval for the population mean weight of newborn elephants. I'm going to state the confidence interval, sketch the graph, and calculate the error bound. So I'm going to go to the next slide where there's space. So as you remember, if we have a 95% confidence level, then our z-score, calculated using the Bogner applet, is going to be almost 2. It's 1.96 to be very precise. And our error bound calculation is as follows. Z times the standard error of the mean, which is our population standard deviation, divided by the square root of our sample size. So let me plug the information into our formula. So with this calculation, we've determined our error bound is 4.16 pounds. So what does that mean? It means that we're taking a normal distribution. We're going to go out 2 standard deviations to the left and to the right of our mean. Our mean weight was 244 pounds. And so now I want to go 1 EBM to the left and 1 EBM to the right of this mean point, x bar, 244 pounds. So if 244 is our mean, and we go minus 1 error bound, that's 239.84 pounds. And if we go up 1 error bound, it's 248.16 pounds. That means that we would be 95% confident that the population mean of newborn weights of cute little elephants would be between 239.84 pounds and 248.16 pounds. So we would say that our 95% confidence level is that the population mean of newborn elephant weights is between 239.84 pounds and 248.16 pounds, and that accounts for 95% of the area underneath the curve. And 95% of the time when we take samples, it's not going to accurately predict the average weight of newborn elephants. Let's quickly preview the students' T distribution before we go. And it's true, beer led to a statistical discovery. English statistician William Gossett from Guinness Beer is the one that developed the students' T distribution. So I'm going to link a video up here that I definitely want you to watch. But here's the key takeaways. William Gossett used to work for Guinness, as in Guinness Beer, and he found using big samples tedious when he needed to use the normal distribution. At Guinness, you couldn't publish any academic papers under your own personal name, so he signed papers just as student. So the T distribution came to be known as the student's T distribution. Let me visually explain the differences on the next slide between a normal distribution and the student's T distribution. Visually, the student's T distribution is very similar to the standard normal distribution, right? The mean is still 0 and it's symmetrical about the mean. However, more probability is under the curve towards the tails of the distribution, so it looks thicker at the ends of the distribution, right? The exact shape, though, is going to vary depending on a value called the degrees of freedom, which we'll shorthand as DF. As DF increases, the student's T distribution becomes more and more like a standard normal distribution. So law of large numbers applies. The larger our sample size, the higher our degrees of freedom, and the more the student's T approximates the standard normal distribution. The best part about using this distribution is you do not need to know the population mean or the population standard deviation to use this. So it's pretty usable in the real world. So I want to give you a quick preview. We're going to still calculate error bounds in a very similar way, except we're going to use the student's T to do so. So instead of calculating a z-score, we'll calculate a t-score. So just know that the T distribution approximates what we call the T distribution for a particular degrees of freedom. And you calculate degrees of freedom very easily. It's just your number in your sample minus 1. So if we had a sample size of 20 items, our degree of freedom would be 20 minus 1 is 19. And we'd write the distribution as capital T approximates lowercase t 19. And we can use an app, I'll show you on the next slide how to access it, to calculate a t-score. And here, instead of using the population standard deviation divided by the square root of n, you're allowed to use the sample standard deviation divided by the square root of n. We're going to follow the very same process. The format for the confidence interval never changes. X bar minus EBM, X bar plus EBM. And Bogner has an app for this. Bookmark this, bit.ly.bognert. Again, this is case sensitive. All you do is enter your degrees of freedom, you enter your alpha, and you'll get X returned as the appropriate t-score you need to use. So again, the top 3 takeaways from this video, it's not comprehensive, but it's good to review. Start making sense of this visual and how this maps onto what you already know about the normal distribution. Here's the formula we're going to use when calculating the EBM for when the population standard deviation is known. And I know it's a little bit hard to see here in the video, but go back in the video. You want to practice writing results using this format. We estimate with blank % confidence that the population mean of very explicit description right here of your variable is between lower value, upper value, and don't forget to include your units, okay? All right, thanks so much for your attention. Thanks to everybody who's helped out, and I will catch you in the next video.